Video, let me try to give a proof of fundamental theorem of calculus that we have described in my previous video. As I have also mentioned that a proof of fundamental theorem of calculus depends on the domain additivity for Riemann integral, which we have stated, and I would not prove it rigorously in a video, but I will leave it as a reading exercise, as an optional reading exercise for you to go through. I'll write down a proof and will upload it sometime during the classes. Okay, so let's recall what does domain additivity say. Here we have taken only one part which will be required to prove the fundamental theorem of calculus. And what is the part? If f is an integrable function on the interval ab, and if c is a point in the closed interval ab, then f is integrable on the smaller or the subintervals of AB given by the closed intervals AC and CB. And in this case, most importantly, we will also have this equality, that integral of f in the closed interval AB is the sum of integral of f over the closed interval AC and over the closed interval CB. Okay, so there is one more thing that I wanted to tell you before I went on to proceed for the proof of fundamental theorem of calculus. So we have always seen that our closed intervals AB is of the form where A is less than B, or at least A is less than or equal to B. But what happens if we take a closed interval BA where it is given that A is less than B, that is the lower index is bigger than the upper index. So we have not seen how do we define this kind of an integral. So this is a convention that we are going to follow. We know how to define the integral in this case if we write it this way, and we will just define this integral as negative of the known integral. So this does not follow from any of our proofs or any of our theorems or results that we have proved or even stated when we were discussing the Riemann integrals, but it is just a convention that we will keep in our mind as we go on. So here let me write down the statement of the fundamental theorem of calculus, the first part. So what did it say? It's told us that if f is a real valued bounded function on the closed interval, if this function is integrable on AB, then the function big fx, which is defined over the interval closed interval AB as well, this function given by fx as takes the following value. So what is the value? So the value is integral a to x ft dt. We have made sense of this integral previously with the notion of domain additivity. So it says that if small f is an integrable function, then this function big f is continuous, and we said that it should satisfy some kind of a Lipschitz condition, which I will show right away. And also if small f is continuous at a point C in the closed interval AB, then big F is differentiable. Let me write shorthand. Differentiable in differentiable at the same point C. At the point C, differentiable at C, and you will ask what is f prime c. This is given by exactly small f of c. Okay, let me try to prove this. So first we will show that the function bgif is continuous. Now what do we have? We know that small f is integrable. So this means that small f is bounded. And what is the definition of a bounded function? There exists alpha bigger than or equal to 0 such that mod of fx is less than or equal to alpha for all x in AB. For all x in AB. Okay, fair enough. So now if I want to show that bgif is continuous, then I should definitely look at this quantity somewhat closely. And what is this quantity? This quantity is given by 1 by x minus c. Okay, so what was fx? Sorry, so fx was a to x ft dt minus this is simply f of c. So what is f of c? This is c to x, or this is I'm sorry, a to c ft dt. And by domain additivity, what we see is that this is nothing but c2x ft dt. So here it can so happen that c is less than x, or it can so happen that c is bigger than x. We do not care. We know how to define this integral in each of the cases. So let's proceed now. So we look at what is modulus of fx minus fc. So this is the thing that we are interested in when we want to deal with continuity of a function. So this is nothing but modulus of integral c to x ft dt, and we have one of our order properties which says that this is less than or equal to integral c to x ft dt. Now t always lies inside the closed interval AB, and because we have proved this used this boundedness, so we can write that this is less than equal to alpha times x minus c. So how did it go? So we would just write it as, so this is less than or equal to alpha times integral c to x, and this is 1 dt. We know what is integral of 1. This will be either c minus x or x minus c, depending on whether x is less than c or x is bigger than c. So this is good enough for us, and this is the Lipschitz condition that we were looking for. So now if you take a sequence xn converging to c, so this then goes to 0. So that means that fxn minus fc has to be converging to 0. So this proves that this function is continuous. Next, what we want to show? We want to show that if f is continuous at c, then bgif is differentiable. Well, let us try to prove it. So to show that, so let us try to prove it rigorously. So what do we do here? So we define a function. F1. So there is another function that we are going to introduce to you for the proof of the fundamental theorem of calculus. And how is this function defined? So f1x is given by fx minus fc divided by x minus c. Of course, in this case we should want that x is not equal to c. This is indeed the case, and small fc simply if x is equal to c. So note that to prove that f is differentiable at C, it is enough to show that F1 is continuous at C. So and this will also prove our claim that big F prime C is equal to small f C, and all these things follows from a very nice result. So very nice result in differential calculus. So this is called Carathéodory's lemma. I am sure that you have seen it in your calculus 1 course. If not, just feel free to write to me. I will make a very short video on this. Okay, so we want to show, to show that f1x is continuous, and we follow the exact same argument, or similar argument. We have to consider the term f1x minus f1c, and note that what is f1x, we know what is f1x, so this is 1 by x minus c times fx minus fc. What is fx? Integral from a to x ft dt minus integral c to x ft dt. And what is f1c? This is simply minus small f of c, and small f of c I can be a little bit more fancy and write it as 1 by x minus c c2x fc dt. So fc is a constant, so this will come out, and this integral is going to be x minus c, so this will get cancelled and you will get f of c. So this is the argument. So let me write down in this fancier form. So integral from c to x f of c dt. Now, so here this is from a to c. Okay, so now this is going to be 1 by x minus c integral c to x ft dt minus 1 by x minus c integral c to x f of c dt. So then this is 1 by x minus c integral from c to x ft minus f of c dt. I hope you are following, and this is exactly how we wanted things to go. You will see in just a while. So let me try to check what is f1x minus f1c. If modulus of that, this is equal to 1 by modulus of x minus c times integral, or modulus of integral c to x f of t minus f of c dt, and this is by one of our order properties, less than or equal to 1 by x minus c integral ft minus fc modulus of that dt. Now we want to, and okay, so here the integral goes from c to x. Fair enough. Now we know that this t that lies somewhere in the interval c to x, so t belongs to the interval c to x, and we are not going to forget this. But we have not used the fact that small f is continuous yet, so let us use this fact now. Since small f is continuous at the point c, given epsilon greater than 0, there exists a neighborhood positive number delta greater than 0, such that x minus c less than delta implies that fx minus fc is less than epsilon, right? So here we fix epsilon greater than 0. So by this condition, by star, by star there exists delta greater than 0, such that whenever x minus c is less than delta, we have if x minus fc is less than epsilon. As I said, we are not going to forget this fact that t lies in the interval. So whenever if x minus c is less than delta, modulus of x minus c is less than delta, modulus of t minus c is also going to be less than delta. So let me write down x minus c less than delta implies mod t minus c less than delta, and that implies mod ft minus fc is less than delta. So this aside, we see that this quantity is less than or equal to epsilon whenever x minus c is less than delta. So this shows that f is continuous. Big f1x is continuous, and by this follows from Kara-Theodoris lemma, as I have mentioned, that this means that f is differentiable at c. Okay, it's continuous at c. So differentiable at c, and also that f prime c is equal to small f of c. This completes the proof of the first part of our fundamental theorem of calculus. So let me also use the same video to prove the second part of the fundamental theorem of calculus. So what did it say? It said that if f is a function from ab to r that is integrable, if it is integrable, so if f from AB to closed interval AB to R is differentiable, and f prime is integrable, then what do we have? Then we have integral AB f prime x dx is equal to fp minus f of a. This is what you have been doing in your high school, and you are now going to see a formal proof of this fact that that you have seen so many times. So we have to do this integration. And how do we do Riemann integration? The first step is to choose a partition. So let P be a partition, x0, x1, xn be a partition of AB, of the closed interval AB. So what we are given? We are given that f is differentiable on the closed interval AB. So we can apply our mean value theorem. So to make things shorthand, I am going to refer to it as MVT in lectures to come. Okay, so what does mean value theorem now tell us? It says that for each I there exists Ci in the open interval xi minus 1 xi with f of xi minus f of xi minus 1 is equal to f prime ci times xi minus 1. So note that where do we apply the mean value theorem? So we are given that f is differentiable on the whole closed interval, and that will also imply that the same thing f is differentiable on xi minus 1 xi for all I. I'm sure that you are following me. And now what we are going to do is that so this is true for all I equal to 1 to n, and we are just going to sum these quantities up I equal to 1 to n f of xi minus f of xi minus 1. We have seen this kind of sums before, and this is summation f prime ci xi minus xi minus 1. So this sum also goes from 1 to n. Okay, so now if you look at it carefully, you will see that you will get fb minus fa at the end of the tunnel, and here the sum we are going to do some estimation and among other things. Okay, so now we have this partitions, we have this ith subintervals, we have this subintervals xi minus 1 xi till xn minus 1 xn, where as always x0 is equal to a and xn equal to b. So let us look at what is f prime ci. See, if I want to compare this with mi, small mi f prime, we can surely say, we do not know whether f prime ci is equal to small mi of f prime, but we can surely say that this inequality is true, because small mi f prime is of course the infimum of all the values that f prime takes in the interval small xi minus 1 small xi, and this is by similar argument less than or equal to big mi f prime, and this is true for all I. So this will give us, jumping a step, but I am sure that you are going to follow what I intend to mean. So xi minus 1 is less than or equal to summation f prime ci xi minus 1, and this guy, so this is summation I equal to 1 to n, and this person is less than or equal to summation I equal to 1 to n big mi f prime times xi minus 1. Now what is this quantity? This quantity is nothing but, with respect to the partition that we have taken, this is LP f prime. This quantity we have seen that this is exactly equal to fp minus fa. So let me write down fp minus fa, and this is again less than or equal to up f prime. But we started with a partition, but we did not impose any condition. So see, our first statement was let P be a partition of AB. So this inequality is, but then this inequality is true for every partition. This inequality holds for every partition P of the closed interval AB. So by taking supremum here, we will see that okay, so let me write down the step one last time for you. LP f prime, where the supremum is taken over the set of all partitions P of AB, is less than or equal to fp minus fa, which is less than or equal to, here I can take infimum, so this is a lower bound of all the mu p f primes, and then we can take infimum, and we can see that infimum taken over the set of all partitions of the closed interval AB, this inequality also holds. But then this guy is nothing but LF prime. This is less than or equal to FP minus FA, and this is less than or equal to UF prime. Now we allude to the obvious hypothesis that we are given with. So what we are given is that is the fact that f prime is integrable. So since f prime is integrable, we know that LF prime is equal to U prime, UF prime. So that is, f is integrable, so we have LF prime is equal to UF prime, and this has this common value, integral a b f prime, right? So integral a b f prime is less than or equal to fb minus fa. It is less than or equal to integral a b f prime, and it follows that integral a b f prime is equal to fb minus fa. So this completely proves the fundamental theorem, that the statements of all the statements of fundamental theorem, right? So a few remarks are in order, and we will finish this video in a couple of minutes. So the first remark, we want to specify that the proof of fundamental theorem of calculus, I am not writing proofs of fundamental theorem of calculus because I want to regard the fundamental theorem of calculus as one statement. So the proof of fundamental theorem of calculus only relies on our mean value theorem and domain additivity of Riemann integrals. Nothing more, nothing less. Next, we introduce you to the term which is known as antiderivatives. So derivatives. So suppose that I is an interval containing more than one point, so we are not looking for an interval of the form a comma a, for example. We are not looking for an interval of this form. So then what do we do? If from I to R, or so let me reformulate this. So function if from I to R is said to have an antiderivative, if there exists a function big F from I to R such that f prime is equal to f. So as it is clear that the function, so in such a case the function f is called an antiderivative or a primitive or an indefinite integral of the function f that we had started with. So here is the last thing that we are going to do. So we finish with this small lemma. If I is an interval and small f from I to R has an antiderivative, then antiderivative, let's say big F, then F is unique up to addition of a constant. This also you have seen hundreds of times in your high school, so let me just formally prove it for you. So suppose f and g are two antiderivatives of f, so that is f prime is equal to g prime is equal to f. So what does this say? This says that f minus g prime is equal to is equal to 0, and we can allude to the mean value theorem again, which will prove that f minus g is a constant. So this proves the thing. So what I have forgotten here, if there exists a function, so you can for the sake of being totally correct, we could say that there is a differentiable function. Okay, so last but not the least, let us try to summarize what does FTC say. So what does our fundamental theorem of calculus say? So it says that if is continuous not at a point but on a whole interval AB, closed interval AB, then then we know that this function is integrable on every subinterval AX, and if we take this integral and if we take the derivative, we will get back our function fx. So this happens for all x in AB. Conversely, if f prime exists, and not only that, and it is integrable, then what we have seen, we can first take ddx of f, so which is nothing but f prime in our notation. So, and if we integrate it from a to b, then we get small fb minus small fa. So this shows that integration and differentiation is some kind of inverses to each other. And third, how to calculate the antiderivative, this follows from here. So antiderivative of a continuous function small f from AB to R, or this is, as I have said, the indefinite integral is given by integral a to x f, or you may write fx dx. So I did not write the antiderivative. The base term that I could enter here is an antiderivative of a continuous function f is given by integral of a to x, integral from a to x of small fx dx. So we have done everything that we wanted to talk about the fundamental theorem of calculus. We will come back with more in our next few lectures. So till then, goodbye.